Okay, so let's take this. Sigma is again 0 and 1, and L is the set of strings W such that W starts and ends with the same symbol. Okay. So how do we go by designing a DFA for this language? W starts and ends with the same symbol. So give me the high-level idea first. How would you write a DFA for this? Starts and ends with the same symbol. It's like, if you have 1, 0, 0, 1, this is an accept. 0, 1, 0, accept. 0, 1, 1, reject. 1, 0, 1, 0, reject. Yes?
What about the empty string?
Okay, this is a good question. So here, because we're saying starts and ends with the same symbol, so we are implying that
0, 0.
that there will be at least one symbol. That there will be at least one symbol in the string. So that the null string will be rejected. Does not belong to this language. Because it does not start. So, and I agree with you that this is, this way of describing the language is not 100% precise. To make it 100% precise, you may want to say that W is a string that has at least one symbol or is not the null string. It's a non-empty string is a non-empty string that starts and ends with the same symbol. This makes it 100% precise. Okay, but give me the idea. How would you design a DFA for this? Question or answer?
Answer.
Okay.
So I would start with Q0. So we're going to start with our start state, and then from there we're going to branch either a 1 or a 0 path.
Okay, that's good. That's a good start. So basically you will have two paths, one for those strings that start with 0 and one for those strings that start with 1. So you're going to have something like this. So this is my start state, and then I will start either with 0 or with 1. Okay, now I will solve two different problems, but each one of them is easy. And we have already seen something similar. Did we do that DFA for a language that starts and ends with the same symbol? It should be easy. So here we're starting with a 0. Now, what should we have? What should this state be?
Q1.
And what should be the transition on a 0?
Loop.
Loop, because we're good, right? We're starting and ending with the same symbol. So we have a loop on a 0, and this is our accept state, right? Starts and ends with a 0. Then what will happen if we get a 1? You should go to some other state, call it Q2, and this is not an accept state, because we are ending with a 1. So if we stay here, it's not an accept state. Now, what will happen if I get a 0 here? Yeah, go back. Now it's accept. If I end with a 0, it's accept. If the last symbol seen is a 0, I go back to an accept. If the last one is 1, I go to a non-accept. So whenever I get a 1, I go to the non-accept. Whenever I get a 0, I go back to the accept state. Now what should be the transition on a 1 here? Stay there. It's not, it doesn't matter. I'm still not in an accept state. Does anyone have any doubt about this, about the correctness of this? Okay, now that we have done the branch for 0, the branch for 1 is going to be easy. Same logic, but we will, everything will be for a 1, not for a 0. So this is, let's call it Q3, and it's an accept state, and there is a loop on 1 or on 0?
1.
Loop on 1. Then 0 takes me to
Q4,
Q4, which is not an accept state, and I loop on
0.
0, and a 1 takes me back to Q3. Okay? Yes, questions?
Question. This might be just common sense, but what is one symbol if it's just 1 0 or just 1? It stays in the accept state.
Or what if the string consists of a single symbol, like this string?
Yeah.
Will it get accepted or not?
Accepted, I just shoot.
It will get accepted. Should it get accepted or not?
Yes.
According to this definition, we said it's a non-empty string that starts and ends with the same symbol, and this is a non-empty string that starts and ends with the same symbol. Okay? Yeah. So it's by the way, it's always a good idea to whenever you design a DFA to think about the corner cases. You know, those corner cases or trivial special cases, like what will happen if it's the null string, what will happen if I have only one symbol. It's a good idea to always think about this when you design a DFA. When designing a DFA, your DFA, you want to make sure that your DFA will handle these cases correctly. So it's just like writing a program. You want your program to handle all cases, including corner cases and trivial special cases correctly. You don't want your program to crash when the input is too small or unexpected or whatever. Okay. Any questions or doubts about this? Okay, so the reason why I gave this example is to show you that some DFAs may have multiple accept states. So here in this case, the set of accept states is going to be the set Q1, Q3. This is the set of final states or accept states. L is the set of strings W such that the sum of symbols in W treated as integers is a multiple of the sum of symbols treated as integers, and our 0, 1, 2. This is our alphabet. So now we are adding a second symbol to the alphabet. So, sorry, a third symbol to the alphabet. So now we have 0, 1, and 2. Okay. So the number of symbols. So what does this mean? The sum of symbols in W treated as integers is a multiple of 3. So it means that if we have 0, 1, 1, 0, 1, then we just sum the symbol. The sum of these is 3. So this is accept. What if we have 0, 1, 1, 0, 1, 1? What's the sum? The sum is 4, so this is reject. What if we have 1, 2, 2, 1?
6, accept.
So this sum is 6, and 6 is a multiple of 3, so this is accept. Okay? So now we're not counting ones or zeros, we're actually computing a sum. We're looking at the sum, and we would like the sum to be a multiple of 3. Okay, so let's see now what this DFA will look like. How many states do you think there's going to be, given what we have seen? Now, try to make a connection between this example and which example?
The modulus one?
Yeah. So how many states will we have? Yeah, we have 3 states because it's, one state for the sum being 0, mod 3, one state for the sum being 1, mod 3, and one state for the sum being 2, mod 3. And you only have 3 possible values, 0, 1, or 2, mod 3. So, this is my Q0, this is my Q1, this is my Q2. Maybe I need more space. I'm just going to redraw it. I will redraw it. I will redraw the same thing. Q0, Q1, Q2. Okay, now, what should happen? What should happen on a 0?
Stays on the same
Loop.
state.
Yeah, the 0, see, the property that I'm looking for is a sum, and 0 doesn't change the sum. So 0 will always keep it in the same state. Now, what will happen if I get a 1?
Advance.
Yeah, you advance. It's just like 1 adds 1 to the sum, and 1 will add 1 to the sum. Now, what will this 1 do? It will do what?
Back to Q0.
Yeah, it will go back to Q0. Okay. Now the trickiest symbol to handle here is which symbol? 2. Now if I'm in Q0 and I get a 2, where should I go?
All the way to
back
Q2.
To Q2.
To Q2. I got just 2 steps, or it's the equivalent of adding 2 ones. 2 is just like 2 ones. So this is what 2 will do. So it will take me 2 steps to the next. I instead of going to the next state, I go to the state after next.
So Q1 would go to Q0.
So now Q1, so in Q1 I will go to Q2, then Q2 will take me to Q0. So then Q1, the transition on 2 for Q1 would go to
Q0, yeah.
0. Yes. In fact, we are doing modular arithmetic or circular arithmetic, and when you do circular arithmetic, going 2 steps in the forward direction is the same as going 1 step in the backward direction. So 2 steps forward is equivalent to 1 step backward because you are doing circular arithmetic. Now, what's
That's
the
right.
transition that remains?
Q2 to Q1 when there's a 2.
Yeah, so when you have Q2, so it's going to go 2 steps to Q0 and then Q1. So it's like, again, going 1 step backward or in the reverse direction. Okay, now we will need to write the mathematical description of this. Okay, I can get rid of this now. Okay, so the mathematical description of this DFA is U sigma delta and the we did not specify the accept state. We forgot the accept state.
Q0.
Yeah, Q0. Okay, so then Q0 is the start state, and in fact, Q0 is the set of accept states. So this is Q0. So in general, I have a set of accept states, not a single accept state, and this set of accept states in this case happen to have Q0 in it. Okay, so now my Q, that's easy. Q is Q0, Q1, Q2. This is my Q. My delta sigma is 0, 1, 2. Oh, so the trickiest part is delta. So delta of a given state Qi and 0 equals
QI.
QI. Delta of a given QI and the 1 equals QK, where K equals what?
I plus 1 mod is 3.
Yeah, exactly. I plus 1 mod 3. Now delta of Qi and 2 is Q K, where K equals I plus what? Plus 2 mod 3. Okay, in fact, I can write it more concisely. One rule, I can do one rule, delta of Q, I, and J, where J is one of the symbols in the alphabet, equals QK, where K equals I plus what? I plus J mod 3. Okay? So this is for, this is one rule. Yeah, in fact, the good thing about this mathematical description is that if I change the problem so that the sum of symbols in W treated as integers is a multiple of n, then graphically using the transition diagram, how would you draw a DFA with n states, general n? So the power of algebra is that you can represent a DFA in this case by changing what?
The number of states.
So what do I change in the yeah? So in this case, this is going to be this is going to become Q0, Q1, Q2. Take the Qn. N or n minus 1? N minus 1. You're right. N minus 1. And then the sigma, in fact, we can generalize the sigma, even if the sigma is, if your sigma is 0, 1, 2 through m, even the sigma, we generalize the sigma, this is something that you will not be able to express using a transition diagram. Okay, the transition diagram can do the concrete, but it cannot do the abstract. This is abstract. When your sigma is 0, 1, 2 through m, and this is mod n, then this formula is just going to give you the right one equation will give you the transition function for a general difference, and all what you need to do is to replace this 3 with n. So it's going to be I plus j mod n, where, okay, and this sigma is going to be m, and where j equals, j is going to be one of the symbols, is a symbol in the alphabet, so j must belong to sigma. J belongs to sigma. J is a symbol in the alphabet. This is this thing here is a symbol. Any symbol. So that would be 0, 1, 2, 3, a symbol in the alphabet. Okay, questions on this? All right, so what we have covered is the mathematical abstraction and how to handle languages with modular arithmetic. So we have 4 minutes, so let's take another example. This will probably be the last DFA example, so next time we'll start talking about NFAs. So L is W such that W has 101 as a substring. So we would like to recognize the strings that have this substring, this string as a substring. So in this case, if you have 1, 1, 0, 1, 0, 0, this is accept. If you have 1, 1, 1, 0, 0, this is reject. So you have to have a 1, 0, 1 as a substring. Now, how many states do you think this will have? So we start with a Q0, right? Then, necessarily, we should have a path in this DFA. We should have a path that has what in it? So this substring should appear somewhere in the DFA. So we should probably have a path from start state to accept state that has a 101 in it. Okay, and clearly this is going to be my accept state. So this is my Q2, this is my Q3. Now what should happen? So if I get this 101, this is going to take me to an accept state. What will happen if I reach this?
You just stay there.
Loop
Keep on
on
looping.
itself
Stay there.
until it finishes.
Yeah, loop on what? 0 or 1 or both?
Both.
Loop on both because I'm done. I have satisfied the property of the language and I don't care what comes next. So clearly, with this scheme, if the substring appears multiple times in the string that I'm trying to recognize, if the substring appears multiple times, which one am I recognizing here? The first occurrence or the second occurrence, or the last occurrence? The first occurrence, yeah. So I'm catching here the first occurrence of the substring if it occurs multiple times. Okay, now it remains to figure out what transitions I should have on other symbols. So what if I get a 0 when I'm here?
Loop on itself.
Yeah, just stay there because I haven't seen anything yet. So I haven't made any progress towards satisfying the property of the language. What will happen if I get a 1 here?
You go back to
Oh.
0.
I go to Q0?
Yeah,
Yep.
go back.
No.
Oh, no, you lose.
No, I don't go to Q0 because if I get a 1, I have made at least one step towards the goal, right? But there is a 1.
It has to
the
be in a
substring
row.
starts with 1. So I stay here. Okay, now what will look at this.
Oh, I got you, because you're still a 1. Yeah.
If you have a string like this, the first one is going to take you here. Where should the second one take you? You stay there because
Yeah.
you are saying that I have seen the 1, I'm waiting for the 0. But the next doesn't turn out to be 0, it turns out to be a 1, so you stay waiting for that 0. So here, Q1, what Q1 means is that I have seen a 1, and I'm waiting for the 0.
Yeah.
And if I keep getting 1s, I'm going to count this one as the first one in the substring that I'm trying to match. Okay? Then, when you get a 0, you go to this. Now, what will happen if you get a 0?
Go back.
0. Start.
0 start over. Because if I get a 0 at this point, I haven't made any progress, and I should start over and look for the 1. So 0 takes me back to square 1, or square 0, where I haven't seen anything yet. Or I haven't seen anything yet of what I'm looking for. Okay, so is it complete now? So I have 2 transitions here, 2 transitions, 2 transitions, 2 transitions. So this is a DFA that recognizes the language that has a substring 1 over.